Okay, this is the pre-lab or pre-lecture, pre-class lecture for Monday, September 10th. In this in this topic, what we're going to do is really start looking at organic chemistry, and we'll talk a little bit about how organic chemistry is organized according to functional groups, and I'll talk a little bit about what functional groups are. On Friday, we kind of ended talking about the sort of review topics for general chemistry with talking about polarity and intermolecular forces and solubilities. So before we get into really the nuts and bolts of organic chemistry, let's talk about how organic chemistry has been typically organized through the years. And it's been organized according to what are called functional groups. And basically a functional group is just simply a grouping of atoms, so a series of atoms that are attached together that have similar, I suppose we could say physical, but much more important, they have similar chemical properties. And so that's how we're going to sort of organize, and that's how every organic textbook, or nearly every organic textbook, is organized according to functional group. So we have roughly, let's say, 11 million, give or take a million here or there, organic molecules. And organic chemistry would really be difficult to learn, as if it's not already, if you had to learn how each and every one of those 11 million organic molecules reacted. So what we find in organic chemistry is that the groupings of atoms called functional groups have similar reactivity, and so if we know how a functional group reacts, it's most of the time doesn't matter whether it's got 1 carbon or 2 carbons or 10 carbons or 100 carbons attached to it. That functional group acts roughly the same regardless of the groups or how big the molecule is. And that's not always the case, but it does help us organize organic chemistry. So we'll talk first about the 4 hydrocarbon functional groups. And these 4 hydrocarbon functional groups, as the name says, contain hydrogen and carbon. And that's it. That's all they contain. And then we'll get to oxygen and nitrogen functional groups in a few minutes. So the simplest of the hydrocarbon functional groups are alkanes. And alkanes have carbon-carbon single bonds, and that's it. Just carbon-carbon single bonds and then hydrogens attached to those carbon atoms. And alkanes, then there are synonyms for this. Alkanes are sometimes called saturated hydrocarbons. Because they basically contain, with all single bonds, the maximum amount of hydrogen per carbon that you can have. The general formula for an alkane is CnH2n plus 2. So, for instance, this molecule at the end here we'll call ethane. This molecule has 2 carbons and 6 hydrogens. That's the maximum amount of hydrogen per carbon that you can have. Saturated hydrocarbons, these are also actually called aliphatic, which is sort of a synonym for the term saturated. You may have heard the term saturated, and in the next functional group, unsaturated. Unsaturated will mean that they have a double bond. Saturated meaning that they have all single bonds. The saturated term, if you've heard it in context of food and nutrition, saturated fats are basically long chains of carbon atoms with a carboxylic acid functional group on the end that I'll talk about in a minute as well. But these long chains, if they only contain carbon-carbon bonds, that's called a saturated fat, or in this case it's a saturated carboxylic acid that goes to make up the fat. If there's a double bond in here, then it's called an unsaturated fat. I think it's the saturated fats that are bad, quote unquote bad. So alkanes are the simplest hydrocarbon functional group, and we are going to talk about those first. Alkenes have a carbon-carbon double bond in them. And so for alkenes, we have the the two carbons have four things attached to them. And so these are also the ones that are called unsaturated, because if you look at an unsaturated hydrocarbon, what you have is a formula of CnH2n. So I've lost a maximum, two hydrogens off that maximum because I formed the double bond. Now, the differences between alkanes and alkenes, an important difference is the idea of rotation around the carbon-carbon bond, which I kind of introduced for the lecture on Friday. The idea that in an alkane you have, in essence, free rotation around the carbon-carbon bond, so that if you had, for instance, the CH3 group here and the CH3 group and the CH3 group there, that the CH3 group could rotate through these positions. Now, I'm sort of violating something here by saying this is a Lewis dot structure, and I'm sort of treating it in 3 dimensions. And remember, if I'm going to treat it in 3 dimensions, then I have to use this sort of tetrahedral representation. But if I wanted to rotate group X back, I have relatively free rotation around that carbon-carbon bond. So there's lots of different 3-dimensional isomers for alkanes, and they're freely interconvertible, and freely meaning that at room temperature there's usually enough energy to allow us to convert those different 3-dimensional structures, or what we called last time stereoisomers. For the alkenes, though, with the double bond, because of the way the carbon-carbon double bond is constructed, you have the pi bond sitting above the sigma bond, and so this locks that alkene in place and creates what the book calls geometric isomers, and what we called last time cis-trans isomers. So if I have group, let's say, X over on this side and group X on this side, that would be the trans stereoisomer, but I can't move the X group from here down here unless I break that carbon-carbon double bond. So there is no quote-unquote free rotation around the carbon-carbon double bond. And that then leads to the idea of double bonds having the geometric or the cis-trans isomers. Up here for alkanes, we have different stereoisomers, but the stereoisomers, the different 3-dimensional structures, are all interconvertible, and we'll actually talk about that after we talk about naming next for the remainder of this week. So just to show you what I'm talking about here in terms of the free rotation, here's my little models of an alkane. And so what you can see with this alkane is the idea that if I wanted to if I want to rotate so that this green, let's say this is a bromine, moves to the different positions, in an alkane I have the ability to rotate that green atom into the various positions. Now this costs energy, but the energy that it costs is usually available at room temperature, and so that's why we say there's relatively free rotation around the carbon-carbon single bond. On the other hand, if I had a carbon-carbon double bond here, in the carbon-carbon double bond I don't have that ability to rotate around the carbon-carbon double bond because it's locked in position by the 2 pi bonds. So if I wanted to, for instance, have the green atom, and this is upside down for me, the green atom and the orange atom here on opposite sides, I would physically have to break the pi bond And then imagine there's still a sigma bond holding this together. And then I could rotate around the sigma bond and then reform the pi bond to then give me in this case, what would be the trans isomer. So we physically have to break the pi bond to allow then the free rotation around the single bond or the sigma bond, and that's going to take some energy, and so breaking a double bond is very difficult and usually requires fairly high temperatures. Okay, so the idea here is that there are some structural differences between alkanes and alkenes. The third hydrocarbon functional group are alkynes. And so alkynes are carbon-carbon triple bond molecules, again, only containing carbon and hydrogen. The general formula for an alkyne is CnH2n minus 2, so we've lost 2 more hydrogens off of the maximum amount. We normally don't call alkynes unsaturated. Unsaturated really means double bonds, but they are even more unsaturated and contain even less hydrogens per carbon atom. So here's a simple molecule. This is actually called acetylene. So if you've ever seen acetylene torches, it's used as a very highly combustible fuel in welding torches because it burns at a very high temperature. The acetylene is C2H2, and it's got a carbon-carbon triple bond. Now, there are no geometric isomers or no cis-trans isomers available for acetylene. And you may say, why? Because what is the geometry around each of these 2 carbons? It's linear, and so there are no possible 3-dimensional structures for acetylene because the hydrogen atoms are in the same line as the carbons. And we'll talk about alkynes. We'll finish the semester up talking about alkynes. So the fourth hydrocarbon functional group is what's called an aromatic, or sometimes called an aryl or a benzene functional group. And this functional group has 6 carbons in a ring with alternating single and double bonds. And then benzene itself, which is the simplest aromatic compound, has 6 hydrogens attached to the 6 carbons, so it's C6H6. If you replaced one of these hydrogens with something else, then it really becomes an aromatic or an aryl functional group. And your book talks about the fact that you sometimes see AR as a substitute for this aromatic ring. You'll also see, sort of next semester, we'll use the idea of pH as a substitute for this ring. So you might see, if I said, for instance, pH attached to Cl, you might look at the periodic table and say, what's this element pH? Well, it's not an element. Instead, pH stands for this benzene ring that's attached to the chlorine atom. And pH stands for a phenyl, which is basically what we use as a name for a benzene ring that is attached to other things. So aromatic compounds have the benzene ring, the 6-membered ring with alternating single and double bonds. We'll get to this next semester. They were originally called aromatic compounds because they have distinctive odors. One aromatic compound that you may have come into contact with or smelled at some point along the way is something like this molecule is called paradichlorobenzene. It has 2 chlorines attached to the benzene ring. This is what's used in mothballs. There's also, when you take two of these benzene rings and you sort of fuse them together, you get the molecule called naphthalene, which is also has been in the past used as mothballs. So they do have distinctive odors, and that's why they were originally called aromatic. Next semester we'll have a totally different meaning for aromatic, primarily meaning that the benzene ring actually is very unreactive, relatively speaking. So it's usually very difficult to get an aromatic ring to react. So all four of these are hydrocarbon functional groups because they only contain carbon and hydrogen. And the one that's probably the most important, but for a sort of unique reason, are the alkanes. Because it turns out that when we make organic molecules, the alkanes make up the sort of the skeleton of the molecule, and then we hang different functional groups off of that alkane. And so I'll show you that after we go through all of the other possible functional groups. We'll look at some molecules, identify what functional groups they have, and you'll see that basically the functional groups just hang off of an alkane skeleton. So the idea here is that if we know how an alkene reacts, it doesn't matter, and this isn't always true, what other groups are attached to the alkene. Most alkenes will react a certain way. So we only have to learn the chemistry of the alkenes, and then we'll know the chemistry of virtually all the alkenes that we would come in contact with. Okay, in terms of oxygen functional groups, the first are alcohols. And so an alcohol functional group has an OH group attached to a carbon. And it's a carbon with 3 single bonds. And so the alcohol functional group, there's a couple that you may have seen in lab already. The 1 carbon alcohol is called methanol. And the 2 carbon alcohol, which has the OH attached to the 2 carbon, is called ethanol, or also called ethyl alcohol. So these are just 2 examples. I guess a third example would be that we could also have what's called isopropyl alcohol, or in the lab, if you had the unknown 2-propanol. Isopropyl alcohol is what we call rubbing alcohol. So OH is attached to carbons that are basically sp3 hybridized or involved in all single bonds are the alcohols. Now sometimes people will specifically refer to the OH group as a hydroxyl group, but that's looking at the OH itself and not the overall functional group. So the alcohol overall functional group is the OH attached to the carbon. Okay, if we take the alcohol, the oxygen, and we attach it to 2 carbons, we make the functional group called ethers. And so ethers have carbons, sp3 hybridized carbons attached to oxygen. Probably the most sort of famous ether is when you have 2 CH2CH3 groups attached to the oxygen. This is called diethyl ether, or it's also just simply called ethyl ether. And diethyl ether was originally used as sort of a anesthesiology compound early on, because it would be used to sort of knock people out before surgeries or cutting limbs off or whatever they did. The problem with diethyl ether is that it has issues of having a very low boiling point. For ether, the boiling point's about 35 degrees Celsius. And it's also incredibly flammable. So its use in anesthesiology is, well, non-existent now because it's very flammable, and so we don't want the operating room to be catching on fire during the middle of the operation. But that's originally what diethyl ether was used for. There's lots of other ethers that sometimes people will see. Here's an ether where if I take this carbon with the 3CH3 groups attached to it and put it on one side and then put a CH3 group on the other, this is called tertiary butyl methyl ether, or TBME, or it's also jumbled to be MTBE, or it's also called BTEX. And this particular ether is actually a very popular additive to gasoline, along with, of course, the ethanol. But this is added to gasoline to make it burn cleaner in our engines. It does have a small issue that if it gets in the groundwater, it's a little poisonous. So there are issues where if this is in gasoline and gasoline escapes from the tank in a gas station, then we have a small issue where we don't want it to be in the groundwater. And I think somewhere in Tennessee around Oak Ridge, there's probably a couple million gallons of BTEX that's just floating around in the soil waiting to get into the aquifer. And so that's a big environmental problem that people are trying to figure out exactly where it is and how it got there. So ethers, we will talk about those next semester as a functional group. And same thing for alcohols. But in lab, we'll use alcohols and we'll use ethers as compounds. Other oxygen-containing functional groups are a whole class of compounds called carbonyl functional groups. And we've talked about this a little bit in lecture. Carbon-oxygen double bond is what is called the carbonyl group. Now, that's not the functional group. The functional groups are going to depend on what two groups are attached to that carbonyl. On one side, we will always have a carbon, another carbon group, but what is attached here will give us different carbonyl functional groups. So the carbonyl group is a C double bond O. If you took that C double bond O group and you added a hydrogen to the other side, so one's carbon, one's hydrogen, that's what's called an aldehyde. And aldehyde functional groups, usually the aldehydes tend to have very, again, distinctive odors, and many aldehydes are used as ingredients in perfumes and colognes and other molecules that are used for scents and fragrances. A ketone, and notice there's no Y here, that's a pet peeve of mine, is people putting Y in ketone. But ketones have two carbon groups attached to the carbonyl. And ketones also tend to be fairly popular use for fragrances and scents. The simplest ketone has two methyl groups on either side of the carbonyl, and this molecule is actually acetone. So in lab, when we use acetone to wash glassware, this is the chemical structure that we're using. And so the carbonyl group allows water. It basically causes acetone to mix with water, and then these CH3 groups cause it to mix with a lot of the organic compounds. And so that's why we use acetone to clean glassware, because it will basically solubilize the water and the organic material. After it washes away, it has a low boiling point, and so it very easily evaporates from the glass. Acetone is also a major component in fingernail polish remover. Carboxylic acids, if we take one side of the carbonyl group and add a carbon to it, and then put an OH group on the other side, that gives us a carboxylic acid. And so carboxylic acids are acids because they tend to lose this H plus to form the deprotonated carboxylic acid, which has a negative charge on this oxygen. And as we saw last week, the this minus can be used to form two resonance structures here. And so carboxylic acids are Bronsted acids and will donate protons. The last sort of oxygen-containing carbonyl functional group are esters. And so running through the other possibility, if you take the carbonyl and then you take the oxygen and not attach a hydrogen to it, but you attach another carbonyl or another carbon group, then you get this ester, which has a CO group attached to the carbonyl as well as another carbon. And so esters would be things like the ethyl acetate that's in fingernail polish remover. And esters also tend to be in flavorings and fragrances because they do have fairly nice or pleasant smells. If I go back here to carboxylic acids usually don't have pleasant smells, and some of them are just outright rancid. The 2-carbon carboxylic acid is acetic acid. That's what is the major component of vinegar. There are 3 and 4 carbon acids. In particular, the 4-carbon carboxylic acid is called butyric acid. It's called that because it's found in rancid butter. So carboxylic acids, we'll learn, can be converted to esters, and so you can turn a fairly foul-smelling compound into one that's a lot more pleasant. Now, the last carbonyl functional group are amides. And for an amide, what you do is you take the carbonyl functional group and you attach on one side the carbon, and on the other side you attach a nitrogen group. This nitrogen group could be attached to 2 hydrogens. It could be attached to 1 carbon. Put a C group there. Or it could be attached to 2 carbons groups. So these nitrogen can either be 2 hydrogens, a hydrogen and a carbon, or 2 carbons. But the idea is the nitrogen-based group is attached to the carbonyl, and those make amides. If you've studied in biology talking about proteins, proteins have a carbonyl group it has an amide functional group, and they're just long chains of these, where the carbonyl of one chain might hydrogen bond to the nitrogen of another to make your proteins either having like a beta sheet structure or an alpha helix. And so proteins are made up of these amides. They're just long in what we would call a polyamide. I go back here and say that if you take an ester and you create esters that are in long chains, you get the infamous polyesters that are used in fabrics and in clothing. Amines are a nitrogen-based functional group that simply has a nitrogen that is attached to either 2 hydrogens and a carbon group, or 2 carbons and a hydrogen group, or it could also be attached to 3 carbon groups. Of course, if there's 3 hydrogens, that's ammonia. So amines are sort of the organic ammonia types of compounds. And amines, you probably come in contact with those if you've ever, had a piece of fish, for instance, that smells fishy or goes bad. Those are amines that are giving you that type of smell. So these are the functional groups that we'll be talking about over the course of the year. And there's one last one, which is nitriles, where you take a carbon group and you attach a C triple bond N group to it. And so nitriles are actually nowadays are common because the blue gloves that we wear in lab are actually nitrile. They have a C triple bond N attached to a long chained carbon, and that's probably the most distinctive groups that we'll talk about. So all of these different functional groups we will talk about from the standpoint of what their chemistry is, a little bit about physical properties, how to name them, and then how we make that group, what reactions form those functional groups, and then what reactions those groups undergo. So what we can then do is, if we get examples of molecules, we can figure out what kinds of functional groups these molecules contain. And so, for instance, here are some of the examples that if we know our functional groups, we could say, oh, well, this molecule contains this functional group and this functional group and this functional group and that functional group. So here's some examples of some practical molecules, some of which you'll see in lab over the course of the semester. The one you won't see in lab on this slide is what's called capsaicin. So capsaicin is the molecule that causes jalapenos to be hot, or if you make like super hot stuff that you have to sign a contract to be able to eat, because if you die they don't want you to sue. The capsaicin is this structure. And notice that I've written this in the simple line bond structure. So you have to get used to the fact that could you convert this structure into the carbon? This is a CH group, there's CH3 groups there. But looking through this, most of this molecule is actually alkane. And what functional groups do I have? I've got this functional group, which is an alkene. I've got this functional group where the oxygen is attached to 2 carbons. That's an ether. What's the OH group that's attached to a carbon called? That's our alcohol. What's this entire ring called? That's a benzene or an aromatic functional group. Now when we get to carbonyls, I got to look at what's attached on either side. So this is my entire functional group. It's got a carbon on one side and a nitrogen on the other, so it's called an amide. So capsaicin, its chemistry that ultimately gives it the heat that you get from food, is because it has an alkene, it's got an amide, it's got an aromatic ring, it's got an ether, and it's got an alcohol. Okay. How about acetylsalicylic acid? Acetylsalicylic acid is the major component in an aspirin tablet. What functional groups does it have? What's this? Aromatic ring. What's this functional group with the carbon on one side of the carbonyl and an OH on the other? That's the carboxylic acid. What's this functional group? Got a carbon on one side of the carbonyl and an OC group on the other side. That's the ester. So acetylsalicylic acid has 3 different functional groups. And this is a unique molecule because there isn't much alkane in acetylsalicylic acid. Here's naproxen sodium that we'll be using in lab. Naproxen sodium is the major component of an Aleve tablet. So it's got a couple of benzene, it's got a couple of aromatic rings here. It's got an oxygen attached to 2 carbons. So it's got an ether. Over here it's got a deprotonated carboxylic acid. So it's got a carboxylic acid that's deprotonated. Acetaminophen is Tylenol. That's the major component in Tylenol. What do I have? Aromatic ring, alcohol, amide. Here's a couple more. Beta carotene. We'll actually be isolating the beta carotene from spinach in lab. Beta-carotene is a hydrocarbon. It has no other atoms than carbons and hydrogens. And notice that it's got a lot of double bonds in it. And it's these double bonds and actually the fact that they are alternating. We've got a double bond, single bond, double bond, single bond on down the line. All of those alkenes actually make beta-carotene the yellow pigment, or appear to our eyes to be yellow, and that can wait until second semester talking about why that is the case. But this beta-carotene then is an alkene. It's a hydrocarbon, and one of the things that we'll learn about when we use this in lab is beta-carotene polar or nonpolar? Well, it turns out that it's nonpolar because it's made up of just carbon and hydrogen. And then this very complicated molecule is what's called Taxol. When I first started teaching 20-ish years ago, Taxol was starting to be in clinical trials for treatment of ovarian cancer. And Taxol has kind of a unique history because back in the 70s, the National Institutes of Health, what we call the NIH, had a program where people were encouraged to try and isolate anti-tumor drugs from natural sources. And so some natural sources that they used were, they tried to use barks off of trees. They sometimes used sea animals or sea creatures, corals, and so they would find these exotic sea urchins, and then unfortunately the sea urchin would end up in a blender, and they would see whether or not the extract had anti-tumor activity, and if it did, then they would begin to separate the components up until they found the one component that caused the anti-tumor activity, and then they'd have to figure out its structure, because we can't kill a ton of sea urchins to get some anti-cancer drug. They'd have to figure out what the structure is and then try and synthesize that if it truly had the potential to be an anti-tumor drug. Well, Taxol came from the bark of the California yew tree, which is just a scrubby little tree that grows in Oregon, not California. And so they found that bark extract had anti-tumor activity, and when they went through and separated everything, they found that Taxol was the compound that was actually responsible for the anti-tumor activity. Back 20 years ago, it was just starting clinical trials, and actually when I was a graduate student at Duke in North Carolina, one of the professors in the department that I actually worked a little bit with, he was the person that actually determined the structure of Taxol so that then they could begin to try and synthesize it. Now it's used in ovarian cancer, and I believe it's a treatment for some other cancers. But the idea is that all these functional groups give you Taxol's chemical reactions that make it the anti-tumor drug that it is. And so if you want to really test yourself, go through the Taxol and see if you can see or identify all the different functional groups that are in there. Matter of fact, that would make a really good question to start class with on Monday, is how many different functional groups are there in Taxol and what are there? So you can try that. Okay, so functional groups are how we organize organic chemistry, and they are really the essence of how organic molecules react. Because for the most part, we take our molecule and we attach the functional groups to alkanes, and then we get a molecule whose reactivity is totally based on the functional groups that it is attached to it. Now, what I wanted to do very quickly was kind of jump into chapter 3 and sort of set the stage for the first functional group that we're going to talk about, which are alkanes. So, as I've said before, hydrocarbons are molecules that contain carbon and hydrogen, And alkanes are the simplest of the functional groups because alkanes contain carbon-carbon single bonds. And there's different ways to represent alkanes. The line bond structure, which you can think of as kind of a Lewis dot structure. We'll look at the structures here as ball and stick models, which are like my little Tinker Toys that I had before. And sometimes we'll look at the models of alkanes using what are called space-filling models, or where the atoms actually have the van der Waals radii. So these are what the shapes of the molecules would look like. Not balls and sticks, but actual spheres that are kind of smushed together. So these spheres represent the clouds of electron densities around the nucleus. And an ethane molecule, which is CH3CH3, would look like this, except in real life the atoms aren't color-coded. So it would just be this gray blob that has this shape. And we know that alkanes are made up of sigma bonds, and we form the sigma bonds by overlapping the two sp3 hybrid orbitals to make an sp3 sigma bonds. All of the carbon-hydrogen bonds come from sp3 to s sigma bonds. Okay. Now, when we talk about the polarity of alkanes, alkanes are considered to be nonpolar compounds since they're composed of nonpolar, or what we call relatively nonpolar covalent bonds. The electronegativity values for hydrogen and carbon are 2.1 and 2.5 specifically. So if you have a carbon-carbon bond, that's purely covalent because those are pure sharing of electrons. If you have a carbon-hydrogen bond, that's going to be what we call a relatively nonpolar covalent bond. Although there is some unequal sharing between the carbon and the hydrogen, the carbon being more electronegative would be slightly positive, and the hydrogen being slightly less electronegative would be slightly positive. So a carbon-hydrogen bond has a little bit of positive charge on the hydrogen and a little bit of negative charge on the carbon, but for the most part we consider these alkanes to be nonpolar molecules. Now there are going to be 3 or 4 times during the course of the year when I do invoke the delta plus charge on the hydrogen and the delta minus charge on the carbon. Okay, and so we've got the carbon-carbon bond is purely nonpolar, and then the CH are what we call relatively nonpolar. So alkanes are carbons with nothing but single bonds. And so where do you see these kind of in nature? Well, they do make up skeletons that we hang functional groups off of, but alkanes by themselves are going to be things like waxes, oils, components that make up gasoline, natural gas. The sort of mother's milk of alkanes is petroleum, crude oil. That's where most of our alkanes come from. If you looked at a 55-gallon drum of oil or barrel of oil, what you would see that contains mostly alkanes with some alkenes and some alkynes. And so one of the stickers that I have on my car is that my car is a hydrocarbon-powered eco-vehicle, which most people, which only actually one person has ever asked me what that means. It basically means that my car runs on hydrocarbons, which means it runs on gasoline. But that's an appropriate sticker because of the fact that I teach organic chemistry and some other reasons that I won't get into here. So hydrocarbons are actually, the mother's milk of those are petroleum. Now, when we're going to start on Wednesday talking about how to name alkanes, and then we'll get into their physical properties and actually a lot more structural stuff, because alkanes are pretty unreactive, but we will talk about reactions of them. But just to start with the idea of alkanes, what we have is that we can have these chains grow one carbon group at a time. This is what's called a homologous series. We start with a 1-carbon alkane, go to a 2-carbon alkane, go to a 3-carbon alkane, a 4-carbon alkane, then a 5 and a 6, and those can go on up the line. Now, some of these alkanes we actually know or come in contact with every day of our life. So here's the naming of that series of alkanes. The 1-carbon being methane, the 2-carbon being ethane, 3 being propane, 4 being butane, 5 being pentane, 6 being hexane, 7 being heptane, then octane, then nonane, decane, and then it goes up from there. Now, we're going to talk about this naming for the next lecture, but these prefixes tell us the number of carbons in that alkane. And so methane means that it's the 1-carbon alkane. Ethane means it's the 2-carbon alkane. Octane is the 8-carbon alkane. When we talk about alkene functional groups, we'll actually have things like octene, which means it's the 8-carbon alkene with a double bond in it. But some of these you've actually heard of, come in contact with. Methane is the major component in natural gas. So if you're burning natural gas in your house, you're using mostly methane. And a natural gas deposit contains methane and maybe a little bit of ethane and propane. Haven't heard much about ethane, but propane, that alkane, what do we do with it? We typically use it either to heat our house in terms of liquefied propane, or propane, maybe you have a heater at your house that does that, or we use this on our barbecue grills. Butane, butane's mostly in lighters to smoke evil cigarettes. Then pentane and hexane, these are solvents that we use in the lab. Methane, ethane, propane, and butane are all gases at room temperature. And then pentane and hexane are the first liquids. Octane, where have you heard of octane? Well, if you go to the gas station and you buy a particular grade of gasoline, it's rated according to how well it burns relative to octane, or basically an isomer of octane. And so we've heard of these alkanes. They either come from natural gas, and most natural gas is associated with some sort of petroleum oil. That's sort of changing with things like shale natural gas, but that's a topic for another time. So what we're going to do on Wednesday is we'll talk about how we start to name alkanes, not just the simple ones, but how do we name more complicated structures. And there we're going to have to talk about systematic names as well as names that people just commonly use. Okay, so this is what we will sort of expand upon on Monday. So again, if you have any questions, if something didn't quite make sense, ask on Monday, and we'll start with making sure everybody understands the functional groups, and then we will talk a little bit more about alkanes.